Good morning. Good morning to all the people who are attending this virtual conference. And I'm Domenico Prattichizzo. I'm chairing this session on robotics, the first one on robotics. And we have 6 talks. And we will start having this nice discussion on robotics. I don't want to waste time because we will have a nice discussion at the end of each talk. And I would like to introduce the first speaker, who is Gionata Salvietti, and will present a work entitled Soft Rigid Grippers to Exploit Environmental and Embedded Constraints for Food Handling. And welcome, Gionata, and go ahead. Thank you.
Good morning, everybody. So yeah, I will start with my talk. Can you hear me? Yes, yes. Okay. Okay. So this, I'm going to talk about these new possibilities of handling food using a novel generation of soft rigid tents. This work actually started a couple of years ago in our university, at University of Siena, where we started to investigate possible solution with a modular structure that were basically used to design grippers that could interact with people, so with application to collaborative robotics, but also grippers that could easily interact with delicate objects. And the main structure that we developed was the one that you can see here, where the modules are composed of rigid links and soft joints with a tendon-driven actuation, and modularity is at a phalange level, and fingers can be composed of different modules and can be arranged in different ways, so to form these kind of grippers. So the result is very adaptable devices and an intrinsic safety that is brought by the compliance at the joint level. So here you can see a series of grasps that can be achieved with these devices. You can easily reshape the arrangement of the fingers, because fingers are fixed to the palm with a joint that can be manually actuated by an operator. It is possible, due to the mechanical structure of the palm, to control separately two fingers, couples of fingers that are moved through a differential system and can be separately controlled. And you can see the flexibility and the possibility here to deal with the object with very different shapes. Okay, then we came to a very nice problem that actually started from a request in a EU project where we had to deal with fruit manipulation, and then extended to a different kind of fruit and food. So you can see here that typically the fruit comes arranged in boxes like this, and to imagine a robot that can go there and pick this kind of fruit, this kind of robot must be gentle when grasping this, and we have to deal with the problem because you have to actually select and pick only parts of the fruit that are stacked in the boxes. So this problem came from this fruit manipulation. On the right, you see another picture where this is, you can see later, this is a collaboration with a company, and they have to basically pick ingredients to prepare automatically pizzas and hamburgers. And ingredients can come in this kind of configuration, and you have to deal with different problems like sticky objects and the possibility to pick only part of the objects from the bowls. Okay, so our first idea was to actually design grippers that can exploit the capability of soft tents to deal with the environment. So you remember the boxes that I showed before. If you go with your hand, you can use, for instance, the edge of the box to grasp an object without damage it. So the idea here was to actually embed part of the environment directly inside the gripper. So instead of having the necessity to look for environmental constraint, the gripper that we developed, that we call the scoop gripper, has already part of the environment embedded in the structure. So basically, we design the scoop that you can see here on the slide. And this scoop is actually designed with a particular shape of a particular shape that actually is designed to better allow the grasping of objects, and is attached to the palm structure through a soft joints that allows also to have a kind of tilt movement that can be used to actually promote the grasp. So what are the main features of this? Of course, here we deal with fragile objects, so it is really important to use less force as possible to pick them. So when there is the presence of this scoop, it is so most of the weight of the object, once grasped, can be held by the scoop. So actually the role of the two fingers is simply the role of caging the object inside the gripper. And if you see here, we did many tests where we actually measured the torque applied by the motors and actually the forces exerted on the objects. And you can see that to grasp the same object, the force exerted on the object is much less when using the scoop. And this actually is really important because in fluids, there are also damage that are so-called 24-hour late damage, because you cannot see immediately that you damage the fluid, but in one day, there are many, so the fluid can start to become brown and you cannot sell it anymore. So this is really important. The other really important aspect is the fact that you can design new novel strategies to deal with objects that are not very easy to pick with classic grippers. Here, for instance, there is a pile of books, and you can exploit the space between the two books, so to slide the scoop inside the two books, and then you can work with the combination of the finger and the actuation of the scoop, so to pick one of the books from the pile. Okay, here you can see the scoop gripper in action. Actually, in these examples, we designed an handle with the controllers of the two degrees of freedom, actuated degrees of freedom, the flexion extension of the finger and the tilt of and the motion of the scoop. And actually, you can see that you can slide the objects below. Slide the scoop below the objects, and you can achieve so you can achieve different type of grasps, always keeping in mind that we want to exert less force as possible on the object to avoid possible damage. So starting from this idea, actually we had a collaboration with a company in Spain that is called Remy Robotics, where so the goal of this company is to have a completely automated process to prepare pizza and hamburgers. So at the moment, actually, they can produce only two types of pizza and one type of hamburger. And the main problem is that they don't know yet how to manage, how to pick ingredients from both, like in this case. So our idea was to try to design a specific gripper for this kind of problems, and we start investigating the problem of picking single sticky objects from a table. And so the first solution that they were trying were using classic, actually this is not very classic, this is in any case a kind of a compliant gripper, the Robotics-I. But of course, they found that ingredients can come with very different shapes and with very different consistency, also within the same type of ingredients, and they were not satisfied about the results that you could get with the classic grippers. So the idea that we had collaborating with them was to actually take inspiration from our co-gripper design and from the scoop gripper, but instead of having fingers devoted to grasp, we actually keep the finger structure and we specialized the fingertips. And the result was the gripper that we called quad spatula gripper, because actually it's a kind of plate that is composed of 4 different parts. And the idea is that you have the compliance structure of the finger, so that can comply with the environment and can slide below the objects. But you can at the very end you can obtain a solid plate, let's say, which is the combination of the 4. I want you to show and to point attention on the fact that on the bottom right, you can see that we also added magnets on the connection between the parts, and I will show you later why these magnets are really important for this kind of application. So the idea here, you can see the principle of work of the gripper is that you have the finger separated. You can go over the objects, then you can command a closing trajectory, and the combination of the compliance of the finger and the combination of the idea of sliding below the objects allows you to create this plate that can then move the object. So the compliance and the trajectory that the finger can actually perform is a result of a study that we started a few years ago. And the idea here is that so to use the ratio between compliance of joints, sequence of joints, to design the closing trajectory. And so we had a procedure that, starting with a desired trajectory for the fingertip, gives you the combination of the compliances of the single joints, and so you can achieve a desired trajectory. And the good point here is that then you can select and print different joints by playing with parameters of the 3D printer, like in this case the infill density of the soft part. So here you can see that the magnets that I was mentioning before are particularly useful to align the parts of the gripper, and while sliding over below the object, magnets can help in achieve a correct configuration of the plate. You can see here that the objects are simply placed on the table. There is no need to have a precise location for the object, but it's actually the idea of embracing from below, I would say, the object, that gives you the possibility to achieve very different grasps, grasps of very different objects. And we actually test all these real ingredients with our gripper. I want to mention that the fact that all the parts here are 3D printed and are made in plastics is really important for the food industry, because all these parts can be cleaned and can be sterilized and reused, which is not possible if we use different combination of fingers and classic grippers. So you can see here that the best, so we tested with and without the alignment of the magnets, and better results were achieved when also magnets were used. We actually quantified this, and we also tested the influence of the magnets on the maximum payload of the object, and we saw that the payload sensibly increased when using magnets. Of course, the magnetic force contribute with the actuation to the payload, to the maximum payload that can be achieved with the gripper. Another very important feature is that Of course, if you use classic grippers, you have to be really precise when planning the grasp, using the different our system. It's really much bigger, the space that you can use for the location of the object. And you can see here that these are the results achieved comparing the quad spatula gripper with the parallel gripper, where the space where you can leave the object is much higher when the quad spatula gripper is used. So concluding, we are introducing a new generation of soft rigid gripper for handling delicate food, and we are introducing this idea of sliding part of the gripper below the objects, and we are also introducing this idea of using magnetic force when there is necessity to increase, let's say, the precision of these soft parts. And we are actually now investigating the possibility of using electromagnets, so to use magnetic force only when needed, and so to avoid problem when releasing the object. So thanks for the attention.
Thanks, Gionata. A virtual applause to you. And now we are open to questions. I want to remember the attendees that if they want to ask question, they can book, their question by writing in the chat, and then the system manager will give him Alessandro Pilloni will give him the access to the microphone. While we wait for the question, Gionata, I think that a very nice idea is the idea of the magnets, right? Yeah. That in some sense, I would say that also allow to have a more allow to have a less precise control of the fingers, because as soon as you get closer, then the magnets keep the attraction. So it's a sort of a robust control via hardware in some sense, no? Yes. Because can you comment on this?
Yeah, or not? It's so the idea is that you have this kind of magnetic guidance, because of course when designing this kind of 3D printed parts, you have always problem to have a very precise alignment for the closing, because there are many parameters that you cannot correctly model, and there are errors while sliding, and there are many things that you have to take into account. And this idea of having magnets, I think it's really nice and can be extended to very wide range of problem when dealing with these soft structures, because as you were saying, it's a kind of robust approach. And of course, you have to, in the case of the gripper, you have to be, you have to consider that you have also to release the quad spatula. So we tested different combination of magnets with different attraction, with different magnet force.
You are right, because the softness makes the fingers in some sense moving and having less control, less precise motions.
Yes.
And the magnets can take rid of these issues in soft robotics.
Yes.
Yeah, the basic idea is to combine magnetic technology with the softness in novel design of soft/magnetic grippers.
Yes.
Okay, so thank you to Gionata. We have 1 minute, exactly the time to switch to the second presenter. And the second panelist, Gionata, you can unshare your screen. And I would like to invite Sara Marullo to share a screen. And Sara Marullo is going to present a mag gripper, another idea based on magnetic technology, a soft rigid gripper augmented with an electromagnet to precisely handle clothes, by Sara Marullo, Simone Bartoccini, Gionata Salvietti, Zubair Iqbal, and myself. Okay, Sara, you can start introducing the work, considering that you have still 30 seconds in advance.
Okay.
Okay.
Thank you. So hello everyone, I am Sara Marullo, and in this session I will present MagGripper. By presenting MagGripper, we want to propose to approach the autonomous garment manipulation by considering gripper and garment not as disjoint entities, but as cooperating parts of a dyad, which is aimed at successfully achieve the desired manipulation. And MagGripper allows to improve grasp repeatability and precision by design, compensating uncertainties on the target grasping location. And I'm really happy to tell you that we currently have a patent pending on our approach. And here is the outline of this presentation: context introduction, MagGripper description, experiments, and conclusions. So let's suppose that we have to fold a pile of garment. It could be nice to have a robotic assistant helping us in this very boring work. But let's think bigger, to large companies that have to manage a large amount of returns, but also to people with physical impairments that need help. Garments are extremely challenging objects due to their extremely deformable nature. And more specifically, the configuration assumed by the garment after a grasp has occurred is highly sensitive to the locations where the garment has been grasped. And relatively small variations in these locations can result in a significant variation of the configuration assumed by the garment. And this variation can influence the outcome of the task, leading to a possible failures. And on the contrary, grasping the garment in proper locations leads to fast and effective task accomplishment. So let me show you an example. Okay. I'm folding a t-shirt by grasping it just in 3 points. So now, okay. So one of the most urgent needs in current research on autonomous garment manipulation is to achieve a precise and repeatable grasping of garments. And to the best of our knowledge, grippers involved in autonomous garment manipulations usually are not specifically designed for interacting with clothes, which are extremely deformable objects. So our simple but effective idea is to exploit an attractive force between the desired grasping location and the gripper. So to this aim, we can establish an attractive magnetic force between the gripper and the garment. And in this slide, we present MagGripper, which is an augmented jaw gripper embedding an electromagnet and capable of interacting with garments equipped with small metal parts that can play the role of ornamental or brand element, such as buttons, studs, or small plates. And here you can see a short video. MagGripper is an augmented jaw gripper, and in its central part there is an electromagnet mounted on the top of a linear actuator. And activating the electromagnet, a magnetic field is generated, which causes a magnetic force that attracts the metal part attached to the clothes. And due to the attractive motion of the garment towards the gripper, a collision occurs and is detected by a small force sensor, which is located near the electromagnet. And the collision detection triggers the closing motion of the jaws. MagGripper has been realized by means of 3D printing. MagGripper exploits the advantages of both the electromagnet and the jaws. The electromagnet allows to grasp in a desired point, while the jaws ensure a secure grasp maintenance during the manipulation. And to avoid the undesired collisions between the electromagnet and the jaws, but also between the fabric and the jaws, we identified the 3 working configurations. So we have pre-grasping, grasping, and release. During the pre-grasping phase, the electromagnet is the most prominent part of the gripper, so no collisions occur between the jaws and the fabric. Then, when the contact is detected, the linear actuator starts retracing, and the jaws ensure the grasp maintenance. After the desired manipulation, the gripper can be released, the object can be released. So, as previously said, grasping a garment in a desired point is the first condition to be met to achieve the desired manipulation. So we performed experiments with a collaborative robotic arm to test the capabilities of MagGripper. And more specifically, we investigated how the performance are related to the size of the metal plate and to the cloth's weight, which is the role played by the electromagnet on the configuration taken by the garment after the grasp has occurred, and how to compensate possible uncertainties on the estimate of the grasping point. So now the questions are how the number of successful grasps changes by varying the plate dimensions, and what about the repeatability of the grasp execution? We used 3 different metal plates, and we covered the extremity of the end effector with a thin layer of tempera colors to leave a mark about the executed trial. And as you can see in this table, the larger is the plate, the larger is the contacted area. And this is due to the fact that the contact can occur in any point of the metal plate after the attraction has been established. And one successful grasp allows us to make a further consideration, because during that attempt, the garment was successfully grasped, but suddenly fell down. However, the electromagnet had not been deactivated yet, and so the magnetic force was capable again of re-establishing the attraction, and so the contact occurs again, and the garment was successfully grasped. So this suggests that by properly managing the time of the activation of the electromagnet, MagGripper can be used also to recover some failures. The question now is how the MagGripper performance are influenced by the cloth's weight. So we used 4 different garments: a t-shirt, a mid-season pullover, a bib, and a small towel. And object weight and thickness are reported in this table, but in the 5th column, you can see the average distance that was required between the garment and the electromagnet to cause the attractive motion of the garment towards the gripper. So, as you can see, the thickness of the garment is more relevant than the overall object weight. And this is due to the fact that changing the thickness of the garment results in varying the local mass that the electromagnet has to attract. So if the local mass increases, then the electromagnet has to be closer to the garment to cause the attractive motion of the garment towards the gripper. So this suggests that we have to choose the electromagnet according to the needs. But so, for instance, we have to reduce to avoid the overheating. But we have to recall that having an attractive motion between the gripper and the garment is interesting because the gripper does not need to contact the environment to grasp the garment. So this allows to have an intrinsically safer robot environment interaction, but also allows the possibility of performing aerial grasps. The question now is, which is the role played by the electromagnet on the configuration taken by the clothes after the grasp has already occurred? We performed experiments with and without the exploitation of the electromagnet, and we obtained quantitative and qualitative results. Concerning quantitative results in this picture, you can see green marks and blue marks. Green marks are related to the area contacted by the jaw tips without exploiting the presence of the electromagnet, while blue marks are related to the area contacted by the electromagnet, but exploiting the presence of the electromagnet. And as you can see, the distance between the blue marks is about 1/2 the other one. And this is due to the fact that without exploiting the electromagnet, the gripper needs to reach the table before the contact can be detected by the force sensor, while exploiting the presence of the electromagnet, the contact occurs before the gripper reaches the table, and the garment assumes a conic-like shape without unnecessary wrinkles that, in the case of non-exploitation of the electromagnet, were due to the fact that the grasp occurs by sliding the jaws on the table. So this allows to have a more predictable configuration of the garment, and these configurations are more suitable to vision-based machine learning techniques for autonomous grasping manipulation, for autonomous garment manipulation. And here you can see a video showing the difference between grasping exploiting the electromagnet and without the exploitation. The question now is how to cope with pose uncertainties on the target grasping locations. When dealing with grasp planning, it is common to have to deal with uncertainties on the grasping location. And to test the capabilities of my gripper in this respect, we introduced by purpose an error of 1 centimeter along the X and Y coordinates of the estimated grasping point, and 7 out of 10 grasp attempts were successful. This is an encouraging result, yet not very exciting, but the presence of the electromagnet suggests the possibility of developing a novel approach that we called blind grasp. The blind grasp is meant to be a strategy according to which the robot is first commanded to reach the estimated target point, and if the contact is not detected, then the robot starts spanning a small area around the estimated grasping point to exploit the magnetic attraction. So, in conclusions, MagGripper proved to be a suitable tool for autonomous grasping of garments, exploiting the magnetic force to perform repeatable grasp execution, to compensate planar uncertainties on the estimated pose of the target grasping point, and the extended point-like contact that is produced by the electromagnet allows to perform grasps without unnecessary wrinkles, achieving clothing configurations suitable to to vision-based machine learning techniques for autonomous manipulation of garment. Thank you for listening.
Thank you, Sara, also for your virtual applause.
Thank you.
And so now we are open to the questions. So we have a few minutes for questions. If people would like to ask questions, the attendees, please send a note in the chat. So it seems, Sara, if I try to find a connection between the previous work by Gionata and your work that you are presenting here. So basically, Gionata was dealing with the softness of the gripper and the softness of the food, in some sense, handling. You are basically working with the softness of the clothes, okay? Because
yes.
mainly the robot was quite rigid, I would say, but the cloth is definitely super soft, actually deformable. So in this case, whenever you have some softness in your manipulation, you deal with some uncertainty, big uncertainty. And in terms of control of position, control of forces, but basically we are talking about position here in both two works. And what you are doing here, what we are doing in the lab, is to try to deal with this uncertainty by putting a sort of hardware layer that creates a sort of attraction through the magnets to the right point. So instead of using robust, advanced control, and of course, advanced sensing like super cameras detecting the thing like that. We are trying to put some magnetic that realize this, this minimum point of a sort of a cost function where the system goes by hardware. Can you comment something about so where is the idea, where in terms of clothes? So do you think that how the clothes should be changed or should be adapted to work with this technology?
Our long-term vision is to have a synergy between researchers in robotics, researchers in machine learning, and also with producer of garments, because we need to produce novel garments embedding small metal parts, but these metal parts can be buttons, or studs, or small plates. So the innovation from the garment producer will be not so strong, but it will allow us to have a robot-friendly lines of productions that can be used in companies when they have to manage the returns, but also in the home of people.
Like Sara, putting something in the shirt that can be hidden, like in the logo or somewhere, some magnet. And yes. I would also like to add in this kind of discussion while we wait for the next talk, is that so this is a big problem, for example, for companies who are selling clothes via web, like Yux or Zalando, because they have a lot of clothes back because they sell it that then someone does not like, and then can send back the clothes. And then, of course, I mean, I saw big areas, like, really, really big areas where there are all these clothes and they need to fold it again, okay? And the cost of the folding by humans is much more than probably the value of the cloth. And so they are looking for automation of folding, and this is one step in that direction. And I also would like to add, since I'm participating to this work, that We have a patent pending on this idea, and we hope to, because the idea of the patent is always important, because if you have a patent, this is what we learned, then you attract company to put money on your research. So it's a way of opening the research field to money from companies, basically. Even if you don't need, you don't want to sell it, having this patent approach is a way to attract the interest of the company. Okay, there is a question by Alessandro De Luca. Alessandro?
Can you hear me?
Yeah.
Yeah. So my question is, very nice work. Can this hardware be integrated with more conventional motion planning strategies for soft garment manipulation? And I'm referring, for instance, to the work of Carme Torres at UPC.
Yeah, for sure. And in the next future, we will have a collaboration with Carme Torres. So yes, sure.
Okay.
There, the nice comparison is to understand to which extent the cameras with massive artificial intelligence to detect points will compare with the magnetic approach that goes directly to the point. Okay, good. Thank you for your presentation, Sara, again, for the questions. And we are on time, and we move to the third talk of the session. That is by Maja Trumic, Giorgio Grioli, Kosta Jovanovic, and Adriano Fagiolini. And the title of the talk is Stiffness Estimation for Soft Robot Joints Without Force Sensors. Thanks, Maja, for giving your talk.
Thank you, Professor, for introducing me. And hello, everyone. I'm very happy to present you today our method for stiffness estimation for soft robots without using force sensors. So I'm Maja Trumic, and I'm a third-year PhD student from the University of Palermo in Italy and from the University of Belgrade in Serbia. Besides me, there are fantastic researchers, Giorgio Grioli from the Italian Institute of Technology, then Kosta Jovanovic from the University of Belgrade, and Adriano Fagiolini from the University of Palermo. So let me start first with the background. We are working with soft robots that have flexible joints, and on the right part of the slide, you can see two, let's say, most recognizable soft robots that have rigid links and flexible joints. By design, these robots are capable of simultaneously changing their position and stiffness, and that is something that distinguishes them from classical rigid robots. Actually, they are capable of changing position and stiffness thanks to the existence of variable stiffness actuators. Let me now tell you the motivation behind and why we decided to work on stiffness estimation. Actually, while we were doing research on closing the loop on position and stiffness for one pneumatic robot manipulator that you can see here on the right side, we obtained such results that we could notice that if we impose dynamics in the stiffness of this robot, then even by changing the stiffness, our position can stay constant if we actually apply our decoupled nonlinear control of position and stiffness. But during this research, we noticed that to close the loop on stiffness, we need to know what is the value of stiffness. For this paper, for this work, we used to calculate the stiffness. We used mathematical model because stiffness is not measurable. So it means that there is no sensor which you can place on a robot and expect a value, precise value for stiffness. So this led us to the question, how can we know the precise value of stiffness? One way to know it is to use invasive stiffness estimation. This approach is characteristic because it tackles the challenge from the motor side, and it is called invasive because you need to know what is the commanded torque to the motor. And when I say motor, I mean the drive that is inside the variable stiffness actuator. So the pioneering research in this field was done by Fabrizio Flacco, where he proposed in 2012 a residual-based method for flexibility torque estimation. Then he used the recursive least square to estimate stiffness. His research has been followed by work by Menard and others who used modulating functions to directly estimate stiffness. And finally, this year, we proposed one solution that uses unknown input observers to estimate flexibility torque, and then recursively square to estimate stiffness. The advantage of this solution lays in the fact that we do not need velocity measurements, and therefore we do not need velocity sensor. Compared to the work by Menard and others, we tune less parameters, because basically we only tune parameters of a recursive least square algorithm. However, the main disadvantage of all three methods is still the fact that we need to precisely know the parameters of a dynamic model of a motor. So let me now tell you the idea in more details. First, let's say we have a variable stiffness actuator in the antagonistic setup, but we will consider one agonistic drive, in our case, a DC motor. So if we write the dynamic model of a DC motor in a state space form, you see that our states are position and velocity of a motor, and the unknown input is a flexibility torque. Then, according to this model, we design an unknown input observer, which gives us actually and reconstructs the flexibility torque. Once we have a reconstructed flexibility torque, we can use recursive least squares to estimate stiffness. Actually, the flexibility torque can be written as a product of a regressor. Regressor is made of terms that are actually powers of transmission deflection and unknown parameters estimated by recursive least square algorithm. By leaning on the relation between stiffness and the elastic torque, we can easily obtain the expression for stiffness that uses the very same parameters previously estimated by RLS algorithm. The same procedure can be repeated for the antagonist drive, and then in the end we can sum up two local stiffnesses to get a total stiffness of a robot joint. Maybe the most amazing part about this is usage of the delayed unknown input observer. This observer is proposed by Professor Sundaram, and this kind of observer is usually used for fault and attacks detection in linear systems. However, in our case, we actually tend to estimate, to reconstruct our unknown input flexibility torque. The main philosophy behind this is that we need to perform dynamic inversion in the system in order to estimate states and reconstruct unknown inputs. So if we have a linear system like here, we can design an unknown input observer whose equations you can see on this part. And you can see that basically we need to calculate E and F observer matrices. And what is characteristic for this observer is that we need L last output measurements. So what is the role of these delayed outputs? Actually, they allow us to relax conditions for designing the observer. And in our case, we do not need any more velocity sensors. The main advantage is that we can have a complete lack of a priori knowledge about the unknown input, which means that we do not need to know mathematical model for flexibility torque in advance. However, as I mentioned before, the main disadvantage is that we need to precisely know parameters of the dynamic system. Now, the interesting part, let me show you results of experiments. First experiment is done on 1 degree of freedom robotic setup. We used the QB-Move variable stiffness actuator. And the experiment was designed in a way that it has 3 phases. In the first phase, both position and stiffness are changing. Then only position is changing while the stiffness is constant. And finally, position is constant and only stiffness is varying. Here you can see the results. You can notice that in the first phase, stiffness is well estimated, except for the first part where we have some initial error. Actually, this error is due to the fact that the recursive least square algorithm needs some time to update its parameters. Then also you can see that in the third phase, we pretty well estimate stiffness. However, in the second phase, we experience a drift. And this drift is due to the fact that our stiffness is constant. Therefore, we do not have enough excitation for our system. In this case, mean square error for stiffness estimation is 10 to minus 1 Newton meters over radian. And at this point, we were wondering how can we prevent this drift from happening. Actually, we can conclude that at this point, system has been enough excited. So we can assume that parameters of RLS algorithm were well estimated. And at this point, we can stop the update of parameters. So let's see what happens. Because now, since we stopped the update of parameters in 200 seconds, the rest of stiffness estimation is performed pretty nice. And you can see also that the mean square error is now 10 times smaller. We performed these experiments also on a 2 degree of freedom setup to show that this method is also applicable to multiple segment robotic system. And the experiments are designed in the same way. So here you can see results for both the first joint and second joint. You can see that stiffness is well estimated in all the three phases. Also, one interesting thing that is worth noting is that the most challenging part when we estimate the stiffness of a robot is what happens when position is constant and when we only change stiffness. Actually, if you look at a human, it is equivalent to the fact that we only perform contraction of muscles while the position of our arm remains constant. Actually, by following this approach, you can notice that there is no challenge in that case, and that also in the third phase, we can estimate properly stiffness. However, we come to one important question. What happens if we cannot hack a robot? So what happens if we cannot have any information about the commanded torque to the motor? In that case, we need to switch to non-invasive stiffness estimation. The main work in this field was done by Giorgio Grioli and Antonio Bicchi back in 2010. And you can see here on the right side that they used a pretty robust setup where a force sensor is placed between the elastic element and the output link. Furthermore, in this work, only a single joint is considered. And while it is probably possible to extend it to multiple degrees of freedom, there has been no formalized solution proposed. So, what is the disadvantage of this method? Mainly, it is the fact that they need to put force sensors. While for this setup, it is not a huge problem. Can you imagine putting force sensor in such a compact cube, like a cube mover VSA? Therefore, we raised another question. Can we estimate stiffness of a whole robot without using force sensor? And actually, this is now the topic of our current research. Since we want to estimate stiffness non-invasively, we need to approach the problem from the link side. Therefore, we cannot now approach the problem from the motor side because here we have commanded torques to the motor, and that's what we want to escape. And we take into account only the first equation. Our second aim is to estimate the stiffness directly. We know that stiffness can be expressed as a sum of partial derivative of flexibility torque with respect to transmission deflection. And the information about the partial derivative of flexibility torque can be found in time derivative of a flexibility torque. Therefore, if we have information about the time derivative of flexibility torque, we can also extract information conveniently about the stiffness of our robot joint. Let me now tell you steps, how we plan to do it. So first step is to consider robot dynamics. More precisely, we consider the first time derivative of a robot dynamics because here is where we have a first time derivative of flexibility torque. Then the second step is to, you can notice that our unknown input observer is a linear observer. And when we consider robot dynamics, we have some nonlinear terms. So in order to overcome this problem, we need to group all nonlinear terms together with the unknown and together with the flexibility torque, and to assume that is all an unknown input. according to these previous conclusions, we built an unknown input observer. And then once we have estimation of time derivative flexibility torque, we can express it again as appropriate regressor and an unknown parameters P. Leaning on the previous relation between the stiffness and time derivative flexibility torque, we can extract also the information from the very same parameters about the stiffness value. Okay, so here are the simulation results. They're pretty nice and pretty encouraging. So on the left side, you can see the output of our unknown input observer. And you can see that the error of estimation of derivative flexibility torque is quite small. Then on the right side, you can see the result for stiffness estimation. In this case, we considered the 2 degree of freedom robotic setup, and we also assumed that we are using QB move variable stiffness actuators. So as expected in the first part, we have some initial error due to the RLS algorithm, but as time passes, our error converges pretty much to 0 and remains bounded during the time. Moreover, we also performed experiments with 1 degree of freedom. We used the cube, and also as expected, we have some initial error, but then as time passes, this error converges to 0. What's also interesting to note is that estimated parameters of RLS algorithm remain bounded over time. So this is it for me. I'm very happy to be here and to present it to you, and I'm looking forward to your questions.
Thanks, Maja. A virtual applause to you as well, and very nice and interesting work. So again, also in this case, if you want to ask questions, drop a line either in the chat or the question and answer area of Zoom. So Maja, can you comment something about the complexity of this estimator? So is it fast enough? I think so. I mean, from the exactly the plots that you were showing. But can you comment on it? I mean, is there some limitation on the dynamics that you can manage in terms of interaction with the environment, or not?
Yes, actually, if you look at the unknown input observer, we notice that the delay we need to introduce in order to escape using velocity sensor is only 2 samples. So it is pretty fast. But the main issue, the slowest part in this chain is the RLS algorithm. So due to RLS algorithm, we have to wait this 100-200 seconds until it converges properly. Okay. However, if we go back to this once we stop the update of parameters, we still get a pretty good estimation of parameters, so we can proceed even without using RLS algorithm online. So once we have it estimated, we can exploit that mathematical model for stiffness and continue with those parameters.
Okay, thanks Maja for the answer. Now we have a question by Alessandro De Luca. And I think you have the possibility to give the question by voice.
Yes, can you hear me?
Yes, very well.
Professor.
I hope I'm not the only one attending the session.
No, there are 18 attending, plus panelists.
Okay.
We are like 25.
So Maja, very nice. I've seen that you're making good progress on the subject. So I have a question on the delayed input observer. So first of all, I think that you need to know the remaining part of the model for doing this. Second part is you're assuming a linear design. What if, apart from the fact the nonlinear term that you're trying to estimate, if you have I don't know, nonlinear friction in the model, and the delayed observer, I mean, it's not clear to me how much delay you're including here, but if you're using this estimation for control, of course, you may guess that delay is not a good characteristic, I mean, for feedback stability.
Yeah, first, Professor, I'm very happy to see you here and very glad to talk about this. And first, regarding delay, we calculated that delay this unknown input observer introduces is equal to 2. So it is not a significant delay, and I think it would not alter too much stability of the control. However, some further more mature research should be done once this estimator is in the loop with one control. Then regarding the nonlinear part of the system, you're absolutely right. Actually, that is one of the issues. What if we have some nonlinear term or some term that is not estimated properly? At this point, we need to model properly all these terms and to assume that our really only unknown thing is the flexibility torque. However, we actually plan in the future to work on the robustness of this observer and also to explore the possibility of using a nonlinear unknown input observer to deal with such issues. I hope I answered your questions.
Yes, I have one small additional on the last part of the talk. So when you're approaching the problem from the link side, do you need an estimate of the acceleration, of the link acceleration?
No, actually no. Unknown input observer allows me not to use it.
Okay.
Okay, thank you, Maja, for your talk and Alessandro for your question. And now we have to move to the next talk of this session. And I ask Riccardo to share his screen. So this work is a work by Giacomo De Rossi, Marco Minelli, Serena Roin, Fabio Falezza, Alessio Sozzi, Federico Ferraguti, Francesco Setti, Marcello Bonfè, Cristian Secchi, and Riccardo Muradori. And it's a multimodal learning system for action segmentation to control surgical robot. Riccardo, thanks for your talk.
Thank you, Domenico. So this work is a sort of preliminary design of an action segmentation tool based on deep learning to control a surgical robot. So this is a part of, this work is part of an EU-funded project called Sara that I'm coordinating. And it is an example of embodied AI in a very challenging scenario. So I will give you some detail about the project, and then I leave the floor to Giacomo that will give you the technical details about the action segmentation tools. Okay, I would like to show you this video that actually explains better the meaning and the goal of Sara's.
Nowadays, during robotic minimally invasive surgeries, 2 surgeons are needed in the operating room. The main surgeon, who teleoperates the robotic surgery platform, and the assistant surgeon, who uses laparoscopic instruments to provide support during the procedure. The Sara's project will allow the next generation of surgical robots to execute minimally invasive procedures with only the main surgeon, without the need of an assistant, thus obtaining a reduction in costs, a reduction in hospital waiting lists, and an improvement in the efficiency of the health system. Through the collaboration of 9 European partners, including universities, hospitals, and small-medium enterprises, Sara's will develop a new robotic system consisting of a pair of cooperating robotic arms holding off-the-shelf laparoscopic instruments. The Sara system will autonomously perform specific tasks currently carried out by the assistant surgeon during a robotic or a laparoscopic procedure. Since 2018, the Sara's consortium focused on the development of 1. A pair of robotic arms to be fixed directly on the operating table, controlling off-the-shelf laparoscopic tools. 2. a bilateral teleoperation architecture to allow remote control of the Sara's arms by the assistant surgeon. 3. A perception module to recognize the action of basic surgical tasks and to detect organs. 4. A cognitive module capable of collecting the outputs of the perception module and planning collision-free trajectories of the Sara's arms to execute surgical tasks like cutting tissues and threads or holding and moving organs. All these components have been integrated into the first release of the Sara's system. The so-called multi-robot surgery platform is composed of a remotely controlled version of the Sara's arms to be used by the assistant surgeon, cooperating with a commercial robotic system to be used by the first surgeon. Expert urological surgeons tested the multi-robot surgery platform by simulating a robotic-assisted radical prostatectomy (RAP) on advanced human abdominal synthetic phantoms developed during the project. The collected data will trigger the implementation of the next 2 releases of the Sara's system. In the first one, called Solo Surgery, the robotic system will replace the assistant, while the main surgeon performs the operation through the console of the commercial robotic system. In the second one, called Laparo 2.0 Surgery, it will play the role of the assistant, while the main surgeon uses standard handheld laparoscopic tools. Therefore, Sara's multi-robot surgery is the first step towards the next generation of surgical robotic systems, merging artificial intelligence, computer vision, machine learning, and cognitive control for smarter and safer.
Okay, so as you saw in the video, so the goal of the project is to develop what we call the next generation of surgical robotic systems that allow a single surgeon to execute robotic minimally invasive surgery. So nowadays in the operating room, the main surgeon is seated at the Da Vinci console, whereas the assistant is next to the patient. What we like to do in this project is to replace actually the assistant. And so to reach this goal, we need to translate the medical knowledge into an engineering formalism that allow an autonomous system to use and interrogate. Then we had to design a perception module that is able to infer the status, the procedure, and the actions performed by the main surgeon. And it is in this object that we are developing the action segmentation tool based on deep learning. And then we are now designing the cognitive control modules that actually makes the decision about and plan the trajectory of the robots. So, okay, the impact, as you saw in the video, was to decrease the cost per procedure, increase the surgeon awareness, and also to develop a sort of nectar about the use of embodied AI in challenging scenarios. So the Sara's platform are actually 3. So on the left is the standard, how the interventions are performed right now in the operating room. So we targeted the Laparo 2.0 surgery, and another platform is the solo surgery, where, and also in this case, the assistant is no longer in the operating room. In order to train the AI module, we have to collect data that are reasonable. So that's the reason for which we developed the multi-robot surgery, where our robots are again teleoperated by an system, but this teleoperation is just temporary, just to collect the data to train the system. So, and of course, this is quite important because good data allows us to train in the proper way the AI-based control architecture. So, okay, this is just a picture that shows how many things that we have to integrate in our cognitive architecture. So the medical knowledge, the action recognition and prediction tools, a supervisory controller, the multi-robot cooperation, a trajectory planner, and then the robot low-level controller. But of course, at the very core of this cognitive architecture is the main surgeon. So this is the big architecture that we are developing right now. So we have the preoperative data, the anatomical model that we use to create a virtual obstacle. Then we have all the Sara's AI modules for the phase recognition prediction, the action recognition prediction, the tool detection, the scene understanding, and so on, and also the speech recognition. Then we have the Sara supervisory controller that makes decision and takes care of the multi-robot coordination. Then we have the MPC module that actually sends the desired position to the robot low-level controller. And then we have this also the Sara's augmented reality to give more feedback to the surgeons. We also made available a data set for training a system that's called ESAD, for endoscopic surgeon action detection data set. Actually, this data set is a set of real videos, so real surgical procedures. So if you don't like blood, this is not the data set for you. But and now we are also developing another data set on mannequins, so on phantoms. So now I'll leave the floor to Giacomo that give you a glimpse about the preliminary result and experiment that we perform right now.
So, morning, everyone. So we can see here that we have a small piece of the general architecture that Riccardo showed before, because this is just to test a small set of features before the bigger integration, and to see where the cognitive architecture could be improved or further developed. The idea is still to have all the modules, so the AI, the supervisory system, the preoperative data, and of course the surgeon always in control. Whereas this is the action segmentation architecture that we chose to implement for at least the preliminary experiments, and to be further developed again for the proper surgical videos. The idea is to use the well-known ResNet architecture for image analysis, which extracts features from images that we also augmented with motion history images, MHI, that are a trace of the movement along the videos, so to maintain a correlation in the temporal domain between the images. Along this information computed by the ResNet, we attached, literally concatenated the information about the kinematic positions of the robots, both the Saras and in this case the Da Vinci, since we are talking still about the architecture where the Da Vinci robot is involved. Finally, all this information about feature videos and kinematics is processed by a temporal convolution network. And this is a technique that is being employed in action recognition to further analyze the temporal progression of features as we process the entire videos that could last up to 40 minutes, an hour, which is the usual length for a radical prostatectomy, at least the core operation without the preoperative phases. The temporal convolution network is quite a simple architecture, but it's demonstrated its viability, especially in processing long-lasting temporal data, and is easier and faster to train when compared with recurrent neural networks, which are another type of neural network for action recognition. You can see that in the toy dataset that we developed for a pick and place operation, which is actually one of the most common operations that the surgeons must do, like picking needles or pieces of organs or stitches in the scene, where in this case the main surgeon on the left has to pick up a little token to pass it along to the assistant surgeon that has the task of putting in the correct location in the image that corresponds to these colored squares. And this data set has been developed with the characteristics of the laparoscopic surgery, so laparoscopic cameras and laparoscopy instruments, to maintain the same challenging environment that is peculiar of this kind of operations. And then, as you can see, we computed the motion history images that in this case are still, but you can see that we have activations of where the movements occur in the image. When we test this toy dataset, we verify that the action segmentation is operates nominally, so it can detect all the different changes in action among the video. So well, so that we can also try to predict which action is going to occur within a horizon of 1 second with a fairly good accuracy, up to 85%. And also maintaining an edit score, which is actually a percentage of which quality of sequencing the algorithm can produce, literally the subsection of all different labels. And this parameter is also very promising with a high score. Yeah. To maintain the control of the entire system, we have to develop also the supervisory control. In this case, it's quite simplified. It's a simple hybrid automata. Hybrid since it relies on states that depend on temporal, on time domain variables, which is this action A, and also the confidence parameter alpha from the network. But as you can see, the structure is still simplified, but allows us to maintain control of the robot. Finally, the formulation for an MPC, which is a simple simple integrator model, but that is limited by the safety distance that we imposed on the system and the maximum velocity that it can achieve. That depends also on the confidence parameter alpha. So if the action recognition is less confident on the result, the robot moves slowly due to the interaction and the optimization of the model predictive controller. And we can see a quick, very quick video of the tests we performed. In this case, the robot, the surgeon is on the right, and the Sara's autonomous system is on the left. It could pick up the exact time when the action needed to be performed, and it operated the task nominally and recognized the correct square where it needed to put the ring. So the task was performed nominally, and we were quite confident on its result. We also tested, and we can see the graph where the velocity of the robot and the confidence operates in conjunction. So we can see that the robot moves much faster when the confidence is lower. There's just a tiny bit of delay due to the control system. But still, the action recognition is able to perform nominally. In this case, the experiment was to have the robot wait for the pickup line that happened at around the second 25. And still, the robot was able to recognize when it needed to pick up the ring in a correct manner. We also tested the dataset on the action recognition on the most used dataset for this kind of operations, which is the Jigsaw's suturing dataset. It is quite older right now, but it's still one of the most challenging datasets available. And the results were still very good, so much so that we were able to overcome the limitations of previous algorithm and achieve a very high edit score with this architecture. So if you wish to follow us for Sara's project, please let us know. Thank you.
Thank you. A virtual applause to you and Riccardo for giving this talk. So now we have time for a question because we have only 2 minutes left. Okay, so regarding your system, of course, I think that you are taking only data in terms of motions, no, from the camera and things. Are you planning also to have interaction measurements like forces and things like that in the future, or is there something there already?
So we are developing, we had the idea of recording also forces, of course, because we thought there could be a good amount of information coming from how much force is exerted on organs, especially since the target is very, very delicate. The problem is that in current surgical instruments, the measurement of force is still basically non-existent due to the nature of the instrument, the tubular instruments that it is inserted in patients, which also introduces the problem of sterilization. So we developed a small system of strain gauges that operates alongside the axis of the tubular laparoscopy instruments and measures the deformation of the tools. And we have some preliminary results, but they were presented on our publication.
Yeah, actually, we also want to patent the algorithm for calibrating the system because the idea of strain gauges on laparoscopic tools is not new. There is a patent from the Intuitive Surgical, but we are working on the algorithm to calibrate the system. The only drawback is that you can measure deflection along X and Y, but not along the main axis of the tool. So because strain gauges cannot work in compression, actually. So that is the only limitation, but I think that it is very difficult to have a better force sensor in a laparoscopic tools.
Okay, okay. So thank you again for your work. And then it's time to switch and to go to the fifth talk of the session. And the work is by Nicole Daurizio, Tommaso Lisini, and myself. And the title is Hand Guidance Using Grasping Metaphor and Wearable Haptics. Nicole is going to present the work. I would like to ask Nicole to share her screen.
I'm having some trouble in sharing the screen. I think I need to leave the meeting.
And enter back. Okay. So is Riccardo still there? Riccardo?
Yes.
Yeah, okay, so we can keep discussing your work if you want. So going back to the force sensor while Nicole keep track, try to solve the question, the problem of the presentation. So is there a plan to include the force sensing in the AI system, and how much will it improve your prediction in terms of getting a new pattern or whatever you can find in the AI system?
Yes. Okay. So the idea is to use the force and the measurement from the force sensors for, trigger the transition from one state to the other one, but also as a security measure. So the laparoscopic tools are, quite flexible. So it is well possible that due to deflection, you can apply a high force or torque to organs. And using only the kinematics, this is very difficult to detect. So actually, a force sensor is really needed for guarantee the safety of the procedure, not the procedure per se, because the task, you can accomplish the task just by looking at the images and the kinematics, because actually this is what the surgeons are doing with the robot nowadays. But I think that for an autonomous system, it will be mandatory to have this information to guarantee a safe interaction with the environment, I would say.
Thanks, Riccardo, for the extra time for your answer. In the meantime, we have Nicole ready. She already shared the screen, so we are fine. Go ahead, Nicole. Thank you. Activate your microphone.
Okay, here we are. Can you hear me?
Yes, very well.
Okay. So, I am Nicole Daurizio from the University of Siena, and I'm glad to present this work entitled Hand Guidance Using Grasping Metaphor and Wearable Haptics. This work proposes the idea of suggesting hand orientation combining vibrations and an easy-to-learn approach. The guidance approach we propose implements the paradigm what you feel, what you do. Indeed, for providing the user with an immediate knowledge on how to interact with the system, the interface metaphor is based on the way humans grasp objects. So a virtual object and a virtual static wrench are used to orient the hand. The subject is then trained to align the perceived wrench along the gravity. This approach can be exploited in several use case scenarios. For instance, it allows to ask users to orient the hand in a certain way in virtual reality context. Similarly, it makes possible to prepare a subject to orient the hand for a complex manipulation task in case of teleoperation. As you may see in the video, a user is rotating the hand, exploiting vibrating timbals. The goal and the actual orientation are reported on the plot with a blue and a green arrow respectively, while on the right side is the participant using the system. We exploit tiny and highly wearable haptic timbals. Each timbal is composed of a vibromotor enclosed on a 3D printed support. The advantage of wearing a so small device is that we do not have problem in tracking the hand with camera-based tracking systems or similar approaches. Indeed, as you can see in the second video, the same algorithm can be implemented exploiting a leap motion to collect data. In this case, we have that the goal is represented by the green arrow, while the actual orientation is the red one. So, to guide the user hand towards a desired orientation, the system exploits a virtual wrench. So, given a desired hand orientation with an arbitrary fingertips configuration, a MATLAB-based software collects data from a high-precision camera-based tracking system and estimates the contact point's position. The algorithm computes a virtual sphere fitting 3 points, the 3 fingertips. We know it is always possible to find a sphere matching these points. Then, given a desired new hand orientation, a virtual wrench is generated and applied to the virtual object. As soon as the wrench is placed, mathematical computation based on the grasping theory generates the haptic cues. So the timbals vibrate in accordance with the wrench direction. Following the grasping metaphor, the mental connection between the two forces suggests that the target orientation is reached once the two wrenches are aligned. Given that a real object generates real contact forces on the user fingertip, to induce the perception of a virtual object, we should know how to generate equivalent contact forces. So in the first equation, we can see the force and moment balance for a generic object. In our case, in the Grass matrix, we assume an hard finger contact model. This means that we consider only the forces which are transmitted to the contact points, while we neglect the moment. Since the grasp here modeled is virtual, we can assume as starting condition the static equilibrium of the forces. It follows that it is possible to apply an external wrench to the object and compute the contact forces that should be applied to maintain the static equilibrium. We will indicate these forces with the vector lambda. Considering that the vector lambda is then used to let the motors vibrate, it is not desirable to have negative values. So we can use the term ngxc to manipulate lambda in order to maximize the information the subject can retrieve from the haptic cues. In other words, in order to have all the negative values in the lambda vector. Towards this goal, as first step, we consider as relevant all the contact points that can apply a positive force. And then we choose the optimal solution C star in order to minimize the difference between the desired lambda and the computed one. So we get the optimal set of contact forces, lambda star, which is then used to drive the motors. We tested two different policies for the feedback generation. The former generates vibration proportional, which intensity is proportional to the norm of the contact force, while in the second case, the vibration were proportional to to the normal component of the contact force. We can see the selected forces depicted in blue in both figures. So more in detail, considering M the value of the 8th motor. In the first case, we use all the 3 components of the contact force to drive the motors, while in the second case, only the perpendicular one. Additionally, we tested 2 different modalities to inform the user about the reaching of the desired orientation. So in the first case, the vibration intensity was maintained constant until the goal was reached and maintained for at least half second. While in the second case, the vibration intensity was proportional to the actual orientation error. To evaluate the real capability of the system in guiding the user end, we conduct an experimental validation with 8 subjects. We exploit a Vicon system both to track the end configuration and orientation and to record the time needed to accomplish the task. Participants tested all the feedback modalities which are listed in the slide. So they tested norm of the contact force with constant and variable intensity and normal component of the contact force with constant and variable intensity. In addition, to test the user capability in orienting a virtual object following the haptic cues, we propose 2 different grasp configurations. In the first case, 3 contact points were associated with the fingertips of thumb, index, and middle digit, while in the second case, a 4th contact point was added in the palm, approximately between the first and the second knuckle. But configurations were tested using the same wrench set. So we select a set of 12 wrenches pseudo-randomly in order to have 5 wrenches involving a single motor and 7 wrenches resulting in a combination of multiple motors. A comparison among the 2 modalities was carried out with a statistical analysis of the data. With the constant intensity modality, we examined the human capability in following the haptic cues without any information about the actual error. In case of 3 contact points, the success rate was 85% with the F policy and 86% with the F perpendicular one. Similar results were obtained with 4 contact points, where participants failed to accomplish the task in total 28 times, 13 with the F policy and 15 with the F perpendicular one. With the varying intensity modality, all the participants were able to accomplish the task, meaning that they were able to align the perceived wrench with the gravity in less than 90 seconds. Since this work was focused on discriminating the best feedback approach, for the statistical analysis, data were grouped and analyzed by feedback type, so regardless the number of contact points. Results and users' experience show that to give information about the actual orientation is crucial to accomplish the task in minor time. Besides the quantitative results, users' opinion points out an evident preference for this policy. In conclusion, with respect to the current available solutions, our approach introduced some novelties. The most important one is that the end is directly controlled, displaying cues in the most sensitive location and independently from other body parts. In addition, human singularities are avoided by charging the inverse kinematics computation to the brain instead of to an algorithm, and no encumbering device prevents the user hand to be free. Finally, the approach can be combined with any hand tracking system, as we see in the second video. Further studies will be aimed to investigate more in detail the difference between different contact point strategies. Moreover, since in this first stage we discard the rotation about the gravity axis, in future work we plan to add the vibrational patterns to encode the rotation around the gravity axis, so the missing orientation cue. Thanks for the attention.
Thanks, Nicole. An applause to you, virtual, in this case. And this is time for questions. we will start the discussion with Nicole now. So Nicole, basically, so you are talking about guidance of the hand. So the problem is that suppose that you want to orient the end of a human in this way, for example. I mean, I'm here and I want to orient the end in this way. Why? Why I want to orient it? Because maybe I have to rehabilitate, or because maybe I have an operator that have to do some work on an engine, for example, and I'm training, or maybe I have to position my hand to do some teleoperation and to stay in some position. So, and you are using a virtual object with the haptic interface, and in this virtual object you apply a virtual force that is shown on the fingers by using haptics, and then you ask the subject to orient this force towards the gravity, right? So for example, if you show a force in this direction, then, I mean, you display with the haptic display, then you orient in this way. But you were showing only normal forces. So did you, I mean, can you comment on the role of the tangential force? Because we are using vibrations, right?
Yeah.
So it's all intensity, so you cannot show directions at the fingers.
Exactly. The idea was exactly that one. So in our first study, we thought to show the haptic information with vibrations. So in practice, our options were to show the norm of the force or the normal component of the force, because they were the most informative. But we are planning to go beyond this and try to inform the user about the orientation with pressure or with other kind of haptic feedbacks, in order to let the user know more precisely how to rotate the hand, maybe even perceiving the tangential force instead of only the perpendicular one.
And this is the reason why you were showing more than 3 haptic display, because on the hand you were showing 1, 2, and 3, right?
Yes.
Or 4.
Yes.
Or 4. So basically you are displaying on the human hand a vector of forces that has 3 components. Okay, that is the branch on the virtual object. So in order to display, I mean, to have observability in some sense, you need to have at least 3 signals, because you are showing a force.
Yeah.
So if you have only 2, I guess that there is a non-observable directions of the force, and you cannot do it, right? So is the minimum.
Yeah. Exactly. We decided to start with 3 contact points because they were the minimum number of contact points to inform the user about the orientation. Then we tried also with 4 contact points, but we seen that for our work, for the purpose of our work, it was not so different. In fact, as you can see from the results, the difference between 3 contact points or 4 contact points were more or less the same.
Okay.
The rate of success was more or less the same. What was really important actually was the kind of feedback that we gave. So to inform the user about the error or not.
Yeah. Another comment that I have while I'm asking to the next speaker to getting ready. We have 3 minutes and then we go to the next speaker. Well, the other thing that I want to say is that, okay, in general, no, you have to tell me how to orient my hand in some way, okay? So, and for sure you cannot do by voice. So you cannot tell by voice to me, I don't know, the Denavit-Artenberg parameters of my hand. It's impossible, okay? Then you can do, but you can do by vision. So you can display on a screen a hand and just ask me how to put the hand by looking the hand posture. And of course, this is impossible to do if I am an operator and I am by visual, I'm busy looking to someone else and I want to have haptics because I'm busy, because I'm looking to somewhere else and I want to have the haptic guidance. But do you think that would be important to have a comparison between a visual display of guidance of the hand and haptic display. Did you think about it or not?
Yeah, I think that it will be a validation that we can perform. And but actually, I think that the kind of guidance that we implement, it's really informative. And as we saw in these results, when the kind of feedback is well structured, all the participants were able to accomplish the task. So it is really a kind of signal that can transfer the information that we want to give.
And of course, it's a very nice way to approach the problem. Suppose that I'm doing a video game and I have already the displays on my fingers, and then I have to orient the hand in some way. So since the device are already there for other reason, I can use those to orient my hand for some video game. Okay, so thank you. It's time to move to the last talk of the session. I'm inviting Tommaso Vicini Baldi to share his screen and present the work instrumenting handheld surgical drills with the pneumatic sensing cover for haptics. This is a work of Tommaso and Chiara from my lab, and Marco Mandalau is the surgeon working on this kind of drills. Unmute your microphone, Tommaso.
Can you hear me?
Yes, very well.
Okay. Hi everyone, I am Tommaso Vicini from the University of Siena and glad to be here to virtually present this work entitled Instrumenting Handheld Surgical Drills with Pneumatic Sensing Cover for Haptic Feedback. This is a joint work between the University of Siena, University of Perugia, and Istituto Italiano di Tecnologia. The direct access to the patient body represents for sure one of the main advantages of open surgery, but there exist some procedures in which the surgeon tactile perception is affected. Indeed, even if with these procedures the surgeon has the opportunity to directly interact with bones and tissue, some surgical tools, like drills, may limit the haptic perception, probably due to vibration or other limitation. Several researchers tried to address this limitation, integrating sensors into the structure of the drill for measuring and thus restoring the interaction forces. As a drawback, the tool has to be modified. With this work, we present a different solution which does not involve any change in the internal structure of the drill. In fact, we propose an instrumented cover relying on a pneumatic method to measure the contact forces between the drill bit and the bone or the tissue. The great advantage of this pneumatic cover is that it's possible to measure the contact force far from the contact site. The electronic sensing components, in fact, can be located outside the human body, far from the drill bit, far from the drill, having as a result a lightweight sensing system. This is not the case in embedding or instrumenting the drill, the tool, with the standard high accuracy 3-axis or 3-axis torque force sensor. For what concerns the working principle, the sensing structure consists of two concentric cylindrical shells separated by a small gap. The inner shell is rigidly attached to the body of the drill, while the outer shell is the one held by the surgeon. Soft silicone pipes are placed between the two shells to fill the small gap, preventing also any relative motion when no force are applied. The working principle of the sensing system relies on the assumption that the system is under a mechanical equilibrium until an external force acts on the drill bit. Due to the contact between the drill bit and the bone, or the body, or a tissue, the inner shell moves towards the outer shell along the direction of the contact, as you may see from the figure placed in the slide. Depending on the intensity of the external force, the displacement generates a compression of the pipes. This compression is estimated using two pressure sensors, air pressure sensors. In the considered surgical scenario, the torque components are considered negligible, and also the grasp squeezing force applied by the surgeon do not cause any structural deformation of the pipes, thanks to the high stiffness of the external shell, of the outer shell. As represented in the pictures, each pipe is ring-shaped and firmly attached to the inner shell, with one end leak-proof sealed, and the other end of the pipe is connected to a pressure sensor. Forces on the XY plane are measured by a sensor, and another sensor used for the forces along the Z-axis. The two pipes for measuring the XY place force sensor are spaced along the length of the drill, also to prevent possible relative motion between the two shells when no force are applied. Both the shells contain grooves for enclosing the pipes and also to reduce the total width of the device. Taking the advantage of a flange at the lower part of the shell, it's possible also to measure the motion along the Z-axis. I want to spend now a couple of minutes, more than a couple of slides, in presenting the steps that translate the pressures into forces. So, starting from the position system, we filtered the raw pressure value by means of an RC filter, and then, thanks to a quadratic mapping, we transform pressure value into force value. Then we apply the norm and we extract force value, force information. Two steps, two software steps, two software piece. Transform, firstly, the force value in a certain envelope, so we take only the max value of a moving window. I will explain better these steps in the next slides. The results of this first block serve as an input for another block for the compensation of a non-contant offset. The compensation of non-contant offset helps the system, helps the algorithm to recalibrate online the estimation, the measure. It's obvious that for translating pressures into forces, we need a calibration procedure. So for what concerns the calibration procedure and the subsequent validation phase, we exploited an high-precision ATI gamma force sensor for identify this relationship between forces and pressures. We performed the calibration procedures 2 times. One for the sensors measuring the forces along the XY plane, and another procedure, another repetition for calibrating the Z-axis component. For what concerns the Z-axis, the Z calibration, the drill was vertically pushed toward the ATI sensor for a total of 50 contact actions, so that the generated force deforms only the pipe Z. Data collected from the pressure sensor and the ATI were quadratically interpolated using a standard MATLAB algorithm. And then we repeated the same procedure for the other sensor, with the difference that we keep the the drill bit, the drill horizontally. Then we validated this method comparing the estimated force with the pressure interpolation with the ground truth estimated by the ATI sensor in 200 contact points. Since the estimated force value is affected, as I was mentioned before, by the relatively slow dynamic of the pneumatic system, to properly compare our estimated values with the ground truth, we added this compensation. The point is that the system can detect the contact and variation of pressure in a very fast way, but it needs more time to come back to the original state, to the steady state. So we identify when the system is slowly coming back, and we dynamically compensate this motion. Once the relationship between the pressure and the force values have been identified and validated, we tested the proposed system switching on the drill, so adding the noise of vibrations. To compensate the effect of vibration, we added an RC filter, and then we filtered the force value with a moving window of 33 milliseconds, a window that we experimentally identified. In this way, with this window, we discard the downward peaks, guaranteeing a safer error estimation. We are dealing with surgeon and surgeries, so the idea is to be safer than to act in the safest ways as possible. The duration of the moving window, as I was saying, was selected to obtain the best compromise between filter performance and the response delay. In addition to the force sensing system, we developed an haptic ring capable of generating cutaneous and vibrotactile force feedback, with the idea of restoring the tactile perception missing due to the vibrations. To have a lightweight and tiny device, we employed a single servo motor controlling a flexible belt for generating cutaneous stimuli. Moreover, an eccentric mass motor, a small vibromotor, is placed to generate alert. The servo motor generates opposite spinning direction of the gears, as represented in the picture, that translate the belt along the vertical axis and squeeze the finger pulp. An experimental validation was carried out to demonstrate the effectiveness of this combination of sensing system and haptic feedback, and to identify the best haptic feedback to provide the surgeon. And users with different levels of experience, from students to medical doctors, took part in the experimental session. Participants were asked to completely remove a blue rectangle from a piece of plywood using the instrumented drill, wearing the haptic device on the other end. 3 feedback conditions were evaluated: no feedback condition, vibration alert in case of exceeding of a threshold, and vibration alert and cutaneous feedback proportional to the exerted force. 2 parameters were considered as a metrics for evaluation: time to complete the task and impulse, that is the integral of the force over 7.5 Newton over the time interval. 7.5 Newton was selected together with the surgeon as a standard force for drilling a bone. The task was considered successfully accomplished in a time limit of 13 seconds without overreaching the limit of 9 Newton. This limit is a safe limit to safeguard both the sensor and the drill. As you may see in these scatter plots, the participants were able to completely remove the blue color in the time limit of 13 seconds, both with and without haptic feedback. In these plots, we report the experimental evaluation results. For each user, we plot both the time and the impulse for each trial. Moreover, as you may see, the absence of feedback always improve the trial for what concerns the impulse. There is no a clear evidence in the time. In fact, statistical analysis reveal that there is no statistical significant difference in the completion time of the task using or not haptic feedback. This is a good point, it is a good result. This means that the surgeon is not distracted, is not disturbed by the presence of the haptic feedback. So he is focused on the task. For what concerns the impulse of the force over the threshold, in case of haptic feedback, we have a reduction, and the reduction of impulse is statistical as significant. So, supported by the outcomes of the statistical analysis, we can affirm that the haptic feedback can enhance the safety in surgical handheld drill tasks, maintaining the drilling force in a specific range. So, in conclusion, in this work, we presented a novel approach to measure force exerted on bones during drilling tasks in open surgery, and provide at the same time haptic feedback to enhance the task, the operation. In future works, we will test the different feedback policies and location for displaying the cues. Moreover, additional metrics, such as tissue discrimination, will be considered. Finally, the cover will be instrumented with additional sensors, like accelerometer, also to measure the inclination of the drill and improve the calibration procedures. Thank you for the attention.
Thanks, Tommaso. A virtual applause to you as well. And it's time for a few questions. We can start the discussion together. And yes, what I would like to ask you, Tommaso, is that, so you are using a pneumatic sensor, but did you ever think about using some other kind of, you know, like a liquid or some other?
Okay. Yes, in preparatory experiments, we tested a lot of different sensor typologies. We tested the string gauge, flexiforce, high accuracy like ATI nano sensors, but the problem is that, for instance, flexiforce are not so precise, so the calibration procedures requires too much time, and the results are not sufficient precise. For what concerns high precision sensor like the ATI, this type of sensors are really bulky, and we cannot embed a sufficient number of sensors in a drill, making also it comfortable or ergonomically comfortable for the surgeon. So we decide to go for pneumatic sensor, and we tested also liquid. So instead of measuring air pressure, we tested the idea of measuring deformation thanks to liquid pressure, but the outcomes of these preliminary results was not good enough. The problem related to the liquid was in the delocalization of the sensor. Curves and the bending of the pipes generate a lot of noise, a lot of bias to be considered, and we do not have this type of problem with air.
Okay, good. Thanks, Tommaso, for your presentation. Now it's time to end the session. We are on time, so this session was on robotics. We mainly covered soft robots and the control and technology around soft robots. And in terms of application, we worked mainly on medical application. We work on the surgical robots, and the last work by Tommaso on drills for surgery. Okay, so this session ends. Thanks to all of you for participating to the session. We will have now virtual coffee break in the virtual squares that you can access via Zoom by looking to the link in the website or attached here in the chat. And the thread on robotics will follow here with the second session, Robotics-II, at 11:30 in the same place, in the same beach. Thank you to all of you, and see you soon. Bye-bye.